Category O, Lecture 28, Quadratic Duality. Let us start with generalities on graded algebras and modules. In what follows, graded means z-graded, that is, graded by the additive group of integers. We fix an algebraically closed field K and let A be associative and unital K-algebra. The algebra A is called graded, provided that A is a direct sum of homogeneous components AI, indexed by integers, such that the product of AI and AJ ends up in AI plus J, for all integers I and J. A graded algebra A is called positively graded, provided that all homogeneous components are finite dimensional, the homogeneous components of negative degree are zero, and the zero homogeneous component is semi-simple. For simplicity, in what follows, we will assume that A is basic in the sense that A0 is a sum of copies of the field K. For example, consider the algebra A of polynomials in variable x. Then this algebra is naturally graded when the degree I homogeneous component consists of all elements in the linear span of x to the power I. Example 2, consider the algebra of dual numbers, that is the quotient of k of x by the ideal generated by x squared. This algebra is naturally positively graded, with only two non-zero homogeneous components, the degree 0 component, which is the base field k, and the degree 1 component, which consists of the linear span of x. So let A be a graded algebra. A left A module M is graded, provided that it is a direct sum of homogeneous components indexed by the integers, such that the application of AI to Mj ends up in Mi plus j for all integers I and j. Morphisms of graded modules are homogeneous homomorphisms of A modules of degree 0. They are denoted by hom with a subscript A, where the first letter H is a small letter, not the capital one, as usually for the usual hom. So this means that a homomorphism phi from a graded A module M to a graded A module N is a collection of maps phi I indexed by the integers, where phi I goes from the homogeneous component Mi to the homogeneous component Ni. And of course, being a homomorphism, phi is supposed to intertwine the action of A on M. We denote by A gmod with capital M the category of all graded A modules. This category has a family of automorphisms indexed by integers which shift the grading. The automorphism M in triangle brackets is the automorphism of A gmod, which takes a graded A module M and produces the graded A module M and then the small m with triangle brackets. And in this new module, the homogeneous component of degree I is equal to the homogeneous component of degree I plus m in the original module. Similarly, given a homomorphism phi between two graded modules, the automorphism m in triangle brackets shifts the homogeneous component phi I to the homogeneous component of degree I minus m in the outcome. For example, the left regular A module is graded. This is just a definition of the graded algebra. More generally, for any idempotent E in A0, the corresponding projective module AE is also a graded module. Now let us discuss the tensor algebra of a bimodule. Let lambda be a finite dimensional algebra and be a finite dimensional lambda-lambda bimodule. The tensor algebra lambda of beam of the pair lambda comma beam is a graded algebra defined as follows. All negative homogeneous components of this algebra are 0. The zero homogeneous component coincides with lambda, and for a positive integer k, the degree k homogeneous component is the tensor product of beam with itself over lambda k times. The multiplication in this algebra is given by the tensor product over lambda for homogeneous elements. Given a positively graded algebra A, the degree 0 component of A is an algebra, and the degree 1 component of A is of course an A0-A0 bimodule. Therefore, we can consider the tensor algebra A0 of A1, which is a tensor algebra of the A0-A0 bimodule A1. And we have the obvious algebra homomorphism alpha from this tensor algebra to the original algebra A, which extends the identity maps on both A0 and A1. Now let us talk about quadratic algebras. Let A be a positively graded algebra. We say that A is generated in degrees 0 and 1 if the homomorphism alpha from the previous slide is surjective. For example, let A be the polynomial algebra with the natural grading. So the degree I homogeneous component is a linear span of x to the power I. Then A0 is k and A1 is a linear span of x. And the tensor algebra of the bimodule A1 over A0 is the polynomial algebra, and the homomorphism alpha is in fact bijective. Therefore, the polynomial algebra with the standard grading is generated in degrees 0 and 1. Consider now the algebra of dual numbers with a standard grading. Then A0 and A1 are exactly the same as in the previous case, so the tensor algebra of the bimodule A1 over A0 is the polynomial algebra. And the algebra homomorphism alpha is by definition surjective. Therefore, the algebra of dual numbers is also generated in degrees 0 and 1. Example 3. Consider the polynomial algebra with a slightly non-standard grading, where we call the linear span of x to the power I the homogeneous component of degree 2i, where I is a non-negative integer. Then, in particular, A1 is a zero vector space, and hence the tensor algebra of this bimodule over A0 is just the base field, which implies that alpha cannot be surjective. Therefore, the polynomial algebra with this non-trivial grading is not generated in degrees 0 and 1. An algebra A generated in degrees 0 and 1 is called quadratic, provided that the kernel of alpha is generated in degree 2. The kernel of alpha is a homogeneous ideal, so it can be written as a direct sum of homogeneous component. So the requirement that the kernel of alpha is generated in degree 2 means that kernel of alpha as a two-sided ideal in A is generated by the homogeneous component ker alpha 2 of degree 2 elements. Here are some examples. Consider the polynomial algebra with a standard grading. Then we have seen that the morphism alpha is bijective, so it doesn't have any kernel. So the kernel is 0. Therefore, this algebra is quadratic. Example 2, consider the algebra of dual numbers with the standard grading. In this case, the kernel of alpha is generated by the element x squared, which is an element of degree 2, and therefore this algebra is quadratic. Example 3. Consider the quotient of the polynomial algebra kx by the ideal generated by the element x to the power 3. So in this case, This algebra is naturally graded with three non-zero homogeneous components, A0 being the base field, A1 the linear span of x, and A2 the linear span of x squared. Similarly to the previous examples, the tensor algebra of the bimodule A1 over A0 is a polynomial algebra, and in this case we see that the degree 2 part of the kernel of alpha is 0. In fact, by definition, kernel of alpha is generated by the element x cubed, which is an element of degree 3. Therefore, this algebra kx modulo x cubed is not quadratic. Example 4. Consider a finite quiver Q with the vertex set Q0 and the set Q1 of arrows. Let A be the path algebra of Q. Then A is positively graded if we define AI as a linear span of all paths of lengths I. So the path algebra of Q in this case is isomorphic to the tensor algebra of the bimodule KQ1 over KQ0, and hence this algebra is quadratic for trivial reasons. And any quotient of this algebra by an ideal generated by linear combinations of paths of length 2 is also a quadratic algebra. An explicit example of a quadratic quiver algebra is the path algebra of the quiver with two vertices S and E, the arrow alpha from S and E, and the arrow beta from E to S, modulo the relation alpha beta is equal to 0. So this is a relation generated by a path of length 2. So this algebra is quadratic, and we have seen this algebra in relation to category O previously. So now when we have defined quadratic algebras, we can talk about the quadratic dual. Let A be a positively graded algebra, and mu be the multiplication map in A. So this is a linear map from A tensor over Ka to A. Then we can restrict mu to the degree 2 part of mu. So this is the map mu2 from A1 tensor over A0 with A1 to A2. Consider the K dual A0 bimodule A1 dual. Also note by our assumptions, A0 dual is A0. Consider the corresponding tensor algebra A0 of A1 dual. Note that the dual of mu2 is a linear map from A2 dual to the dual of A1 tensor over A0 A1 because of the finite dimensionality and self-duality of A0. This is isomorphic to A1 dual tensor over A0 with A1 dual. So the quadratic dual of A, denoted by A shriek, is the quotient of the tensor algebra of the bimodule A0 over A1 dual by the ideal generated by the image of mu2 dual. So this image consists of elements of degree 2 by definition, therefore this algebra is quadratic. So the algebra A shriek is quadratic by definition, even if A is not quadratic itself. For example, if A is a polynomial algebra with a standard grading, then mu2 sends x tensor x to x squared. So in particular, it's an isomorphism. Consequently, mu2 dual is also an isomorphism, and therefore, if we denote by f the dual of x, the image of mu2 dual is a linear span of f squared. Therefore, the quadratic dual of the polynomial algebra is the algebra of dual numbers in the variable f. So the variable should be the dual of the variable of the original algebra. So why is it called the quadratic dual? So this name is justified by the following proposition. If the original algebra A is quadratic, then the double quadratic dual of A is isomorphic to A. Proof. Consider the short exact sequence. So we take the map mu2 and consider its kernel. So we can write everything as the short exact sequence. The kernel of mu2 is a subspace of A1 tensor over A0 A1, and then this is sent by mu2 to A2. So if A is generated by degree 0 and 1, the map mu2 must be surjective. As we already noticed, the dual of A1 tensor over A0 with A1 is A1 dual tensor over A0 with A1 dual. Hence, we can apply duality to this short exact sequence and get the dual short exact sequence. A2 dual is mapped by mu2 dual to A1 dual tensor over A0 with A1 dual, and this is mapped to the dual over the kernel of mu2. And this is mapped to 0. By the definition of A shriek and the universal properties of the cokernel, the multiplication map from A1 dual tensor over A0 with A1 dual to A2 shriek factors through kernel of mu2 dual, because the multiplication map must have the image of mu2 star as the kernel by definition. And since the quadratic dual A shriek is generated by definition by A1 star over A0, we thus get that the degree 2 component of A shriek is just isomorphic to the kernel of mu2 dual. So if we take the dual sequence again, we obtain a canonical homomorphism from the double dual to A. And this homomorphism is an isomorphism since A is assumed to be a quadratic algebra. This justifies the name the quadratic dual of A. For example, let A be the Quiver algebra of the following Quiver. So we have the vertices 1, 2, and 3, the arrows alpha from 1 to 2, gamma from 2 to 3, beta from 2 to 1, and delta from 3 to 2. And the relations gamma after delta is 0, gamma after alpha is 0, beta after delta is 0, and alpha after beta is equal to delta after gamma. So this algebra is quadratic by definition, so all relations are quadratic. Of course, in the natural gradient, where the degree of each arrow is 1. And the quadratic dual of it is the Quiver algebra generated by the dual Quiver. So for each arrow, we take the dual arrow in the opposite direction. So we have the same vertices 1, 2, and 3. The arrow alpha star from 2 to 1, gamma star from 3 to 2, beta star from 1 to 2, and delta star from 2 to 3. And now we should swap all the original relations into their duals. And this gives us the relations alpha dual after beta dual is 0. This is because we didn't have any relation beta alpha is 0, so we will have this quadratic relation at the vertex 1. Then we had the relation that gamma after delta was 0, so there will be no relation at the vertex 3. And since we had the relations that gamma after alpha is 0, there will be no quadratic relations between 1 and 3, and similarly between 3 and 1. And originally at the vertex 2, we had the relation that alpha after beta is equal to delta after gamma. So now the dual relation in this vertex will be that beta dual after alpha dual is equal to minus gamma dual after delta dual. Of course, this minus, we can rescale the arrows in the algebra to get rid of this minus, but in the natural basis, it should be. So here are the graded Loewe series of projective A and A shriek modules. So A has projectives 1, 2, 1, and then 2, 1, 3, 2, and 3, 2. And the algebra A shriek has projectives 1, 2, 3, 2, 1, 3, 2, 3, and then the projective at 3 is 3, 2, 1, 3, 2, and 3. So the algebra A shriek is much bigger than the algebra A, dimension-wise. Let us now talk about linear complexes of projective modules. Let A be a positively graded algebra, and let us fix a primitive decomposition of the identity in A0 into a direct sum of primitive orthogonal idempotents E1, E2, and so on, En. So for each I, we have the graded projective module Pi, which is A times EI, and its simple top Li. The simple top is concentrated in degree 0. And let P be the direct sum of all these projectives. The category LCP of linear complexes of projective A modules is the full subcategory of the homotopic category of projective A modules, which consists of all complexes such that the homological degree K component of the complex belongs to the additive closure of the module P shifted in degree by K. And this should hold for any integer K. Note that since algebra A is positively graded, if we take two linear complexes of projective modules P and Q, the space of homomorphisms from the homological degree K part of P to the homological degree K minus 1 part of Q is 0. So this is because the module PK is generated in degree minus K, while the corresponding homogeneous part in QK minus 1 is just 0 as a vector space. So there are no non-zero homomorphisms from PK to QK minus 1. So therefore, there are no homotopies between these two complexes. So in principle, the homotopy condition in the definition is redundant. So for example, all projectives Pi from this definition are linear complexes when we consider them as complexes in homological position 0. While if we shift them by 1 in homological position, they are no longer linear because they're generated in the wrong degree. At the same time, if we shift such Pi by k in the homological position and by minus k in the graded degree, we will get a linear complex of projective modules. Let us now discuss the connection between the linear complexes of projective modules and the quadratic dual of A. First of all, let us note that the category of linear complexes of projective modules is an abelian category. Indeed, this category is additive for the obvious reasons. Now, let us note that if we have a homogeneous map from Pi to Pj, such a map is either 0 if I and j are different, or is an isomorphism if I and j are the same. Hence, the kernel of such map is either 0 or Pi, and the cokernel is either 0 or Pj. From this observation, it follows that the category of linear complexes of projective modules inherits the abelian structure from the category of all complexes. Please note that we can consider it also in the category of all complexes because the homotopy condition is redundant in the definition. So for a graded algebra B, let us denote by B GF mod the category of all graded B modules with finite dimensional graded components. The connection between linear complexes of projective A modules and the quadratic dual A prime is given by the following theorem, which is due to Katarina Shtopel, Sergei Ovsienko, and myself. The category LCP is equivalent to the category A shriek GF mod. And this theorem and many other results in this lecture are taken from the paper Quadratic Duals, Cauchy Dual Functors and Applications from 2009. So let us now discuss the sketch of the proof of that theorem. It is quite easy to see that the simple objects in the category of linear complexes of projective modules are exactly the projective modules appropriately shifted in homological position and in graded degree. And first extensions between simple objects in the category of linear complexes are then given by complexes of projective modules which look as follows. So we have two non-zero components, we have two projectives shifted by k and respectively k plus 1 in the graded degree, and some non-zero homomorphism between them. In this complex, the right non-zero component is actually a subobject, and the left component is a quotient, which means that such a complex with Pj k plus 1 being a subobject and Pi k being a quotient, it corresponds to a non-zero homomorphism from pi shifted by -1 to pj, which on the level of A modules means that it corresponds to a length 2 graded A module with top Lj and socle Li. So now we see how it dualizes in the complex world. So here pj is a subobject and pi is a quotient, but for A modules we have that Lj is the top and Li is the socle. So consequence from this is that the Gabriel quiver of LCP is the opposite of the Gabriel quiver for the algebra A. And next observation, the algebra behind the category of linear complexes must be quadratic, because the only condition when we construct a linear complex which we want to satisfy is that we get a complex, and this is a quadratic condition given by the differential in the complex should be 0. So it is natural to expect that the algebra behind the category of linear complexes of projective modules is quadratic. So the Gabriel quiver is the opposite one, which corresponds to the dual bimodule A1 dual, and the algebra behind is quadratic. So it takes some work now to show that this quadratic relation is given explicitly by killing the image of the multiplication map mu2 star. Let us now discuss indecomposable injective envelopes of simples in the category of linear complexes. Let P dot upper I denote the minimal projective resolution of the simple module Li for I from 1 to n. Since A is positively graded, on each step of the resolution, we must go at least one step down, so higher in the grading. So which means that in the homological position K, any summand of P upper I in the homological position K must be of the form some projective PS, so shifted to this homological position, and then shifted in degree by J, where J is less than or equal to K. So in other words, it should be a projective module below the main diagonal in the homological graded picture. And then also because of the fact that A is positively graded, so P dot I has a subcomplex which we denote by P overlined dot I, which contains all diagonal summands of P dot I. So it contains all projectives which are shifted such that the homological shift and the degree shift match. It belongs on the diagonal which defines the linear complexes of projective modules. And we will say that a position is subdiagonal if it is one step below the diagonal which defines linear complexes of projective modules. It is very easy to see that the complex P overlined has no subdiagonal homology. And the main observation is that this complex is the injective envelope of the simple object Pi in the linear complexes of projective modules. And the idea of the proof of this, so we need to prove that this complex is injective. The fact that it has Pi as a subobject is clear from the construction. So we need to prove that the first extension from any simple object to this complex vanishes. We know that simple objects are the shifts of projectives so that they are placed on the diagonal. And using the absence of the subdiagonal homology in this complex P overlined, one should consider a complex representing such an extension, and then in that complex one can change the basis so that the simple quotient pj a minus a is split off with a new change of basis. So here is an example. Let A be kx modulo x cube with a natural gradient the degree of x is 1. Below we will give the minimal projective resolution of the simple A module. So it will not be a diagonal complex. It will have the diagonal part which is overlined and which will be colored in magenta. And we will also show the homology of the original complex and the additional homology of the overlined part. And to show that the subdiagonal homology is zero, the subdiagonal components are given by unfilled circles. So here is the picture. So this is k of x modulo x cubed. We have three components, and this is a simple module in homological position 0 and in degree 0. So it's covered by projective. The kernel is here. So we covered the kernel, and we have one additional component, which is a new kernel, which we now have to cover. But here we have the step 2. So this top is no longer on the diagonal. So again, we take this projective, we have the kernel which is two-dimensional, we cover it, and this continues. So in this complex, so this will be an infinite complex, but only the first two parts are generated on the diagonal. So the overlined part is only the first two steps in this resolution. So the resolution itself, of course, has only homology in position 0 and degree 0, because it resolves a simple module. But when we take the diagonal part, so we delete a big chunk of the resolution, so we get a new homology, which is here. But this homology appears in the position which is on the second subdiagonal, not on the first one. So the subdiagonal position is the first position below the diagonal, and we see that we do not get any homology on the subdiagonal position. So this is an example illustrating the proof on the previous slide. Let us now discuss indecomposable projective covers of simples. So similarly to the linear complexes of projective modules, we can define linear complexes of injective modules. So let n be the graded Nakayama functor for A. So this is given by tensoring with the dual bimodule, but we don't dualize A, we just dualize the finite dimensional homogeneous parts and take the direct sum. So this is a much smaller vector space. Then, of course, the Nakayama functor tensoring with this bimodule is an equivalence between the category of linear complexes of projective modules and the category of linear complexes of injective modules. So similarly to linear complexes of projective modules, in the linear complexes of injective modules, we can consider the minimal injective co-resolution of Li and take its linear part, denoted by the overline. And just the dual argument to the previous slide says that this overlined complex is the projective cover of the simple object II, which is just Nakayama applied to Pi, in the category of linear complexes of injective modules. So if we apply the inverse of the Nakayama functor to this complex I overlined, we will get the projective cover of Pi in the category of linear complexes of projective modules. So let us now define the so-called up and down arrow categories. Let A be a category of complexes of graded modules. We denote by A and then the down arrow the full subcategory of A consisting of all complexes bounded on the right and such that all non-zero homogeneous components of these complexes are placed below a shifted diagonal. Denote by A upper arrow the full subcategory of A consisting of all complexes bounded on the left and such that all homogeneous components of these complexes are placed above a shifted diagonal. Pictorially, the complexes in A down arrow live in this kind of triangular area, so they are bounded on the right, so they are on the left of some vertical line, and then they should be below some shifted diagonal. Similarly, A upper arrow lives to the right of some vertical line and above some shifted diagonal. So let us now define the complex P dot as the direct sum I from 1 to n of the complexes, so this is the inverse of the Nakayama functor, I overlined upper I. So we take the direct sum of projective covers of all simple objects in the category of linear complexes of projective modules. From what we already discussed, we see that the vector space of all homomorphisms from P dot to P dot shifted by k and minus k over all k greater than or equal to 0. This vector space has a structure of a positively graded algebra, which is moreover isomorphic to the opposite of the quadratic dual of A. So the homomorphisms in this definition, they are taken in an appropriate derived category. So for example, if we consider the definition of P and apply the functor n, we end up in the category of linear complexes of injective modules, so we can take the homomorphisms in the category D plus A gmod. And a little bit about the proof of this corollary. It of course follows directly from the description of the category of linear complexes using the algebra A shriek, and the fact that P consists of projective covers of simple objects in this category. Consequence of this is that the algebra A shriek is isomorphic to the algebra of diagonal extensions of simple graded A modules, because these complexes which define the algebra are essentially the linear parts of the injective resolutions of simple A modules. So for example, if A is kx modulo x cubed, such that the degree x is 1, and let L be a simple A module. So we saw, when we had an example of constructing the diagonal part of the projective resolution of the simple module L, that it only had two components. So the diagonal extensions of L are of degree 0 and 1. So the diagonal extension algebra is two-dimensional. It has one component of degree 0 and one component of degree 1. So it is clearly the algebra of dual numbers. And this is exactly the quadratic dual of kx modulo x cubed. So now let us discuss quadratic duality functors. Let A be a positively graded algebra and consider its quadratic dual A shriek. So consider the down arrow category of A gmod and the up arrow category of A shriek gmod. It is easy to see that taking homomorphisms from our complex P dot gives rise to a functor from this down arrow category to this up arrow category. Of course, when we speak about homomorphisms, we mean homomorphisms taken in the graded sense, that is, with respect to all shifts of this complex, both in grading and in position. So let's denote this functor given by taking homomorphisms from P dot by K. And of course, we can also tensor with P dot, and again, taking all the shifts and so on. And this gives rise to a functor from the up arrow category to the down arrow category. So we denote this functor by K prime, and we call K and K prime the quadratic duality functors. And now we can formulate the quadratic duality theorem, which is due to Katerina, Sergei, and myself. The pair K prime K is an adjoint pair of functors. So K intertwines the homological shift by I and the graded shift by J in the following way. K after homological shift by I and the graded shift by J is equal to the homological shift by I plus J, graded shift by minus J after K. So K prime intertwines these shifts in exactly the same way. K sends A simples to A shriek injectives, and K prime sends A shriek simples to A projectives. So after the preparation work which we done, this is not a very hard result. So a junction more or less follows by definitions because the functors are given by taking hom and tensoring with the same object. The rules of commutations, they follow from the diagonal nature of A shriek, realized by the category of linear complexes of projective modules. That K sends A simples to A shriek injectives follows from the description of injective objects in linear complexes. They're just linear parts of injective resolutions of simples. And that K prime sends A shriek simples to A projectives follows from our descriptions of simples of simple objects in the linear complexes of projective modules. They're just exactly the projective A modules. So here are some further properties of quadratic algebras. So let D be the usual K duality. Then the quadratic duality functors have the following property. If we assume that original algebra A is quadratic, then the quadratic duality functor K for A shriek op is just the conjugation of the quadratic duality functor K prime for A by duality. So there is a connection between quadratic duality functors for A and A shriek, which is given using the vector space duality. Another property of quadratic algebras is the following theorem. Assume that A is quadratic, then the quadratic duality functors induce equivalences between the following categories. So first of all, the intersection of the linear complexes of projective A modules with the down arrow derived category of A GF mod and A shriek GF mod intersection with the up arrow derived category of A shriek GF mod. And similarly, A GF mod intersection with the down arrow category and the linear complexes of injective modules for A shriek intersection with the up arrow derived category for A shriek. So let us consider one more example. So let A be the path algebra of the following quiver. The vertices 1, 2, 3, and 4, the arrows alpha from 1 to 2, beta from 2 to 3, and gamma from 3 to 4. Modulo the relation gamma after beta after alpha is 0. So here are the projective resolutions of A simples. So L1 is covered by P1, the kernel is P2 shifted by -1, and the next kernel is P4 shifted by -3. So this shift by -3 is a problematic thing because this lives strictly below the diagonal. This is not a linear complex of projective modules. So L2 is covered by P2 with the kernel covered by P3 shifted by -1, L3 covered by P3, the kernel P4 shifted by -1, and L4 is just P4. So the corresponding linear complexes, which are the injective objects in the category of linear complexes, are, so P2 shifted by -1 maps to P1, so the P4 part just disappears, and the remaining complexes are as here. So P3 shifted by -1 goes to P2, P4 shifted by -1 goes to P3, and then just P4. So these are the injectives in LCP. We know that A shriek has a dual quiver, so we have 1, 2, 3, and 4, with arrows alpha dual from 2 to 1, beta dual from 3 to 2, and gamma dual from 4 to 3. And here are the injectives. So the injective in 1 has only 1 and 2. The injective in 2 has only 2 and 3. The injective in 3 has 3 and 4. And the injective in 4 just has 4. So this means that the algebra of diagonal extensions, which is A shriek, should be the quotient of the Quiver algebra by the ideal generated by alpha star after beta star and beta star after gamma star. This is exactly the quadratic dual of this quiver. Here are some questions for PhD students. Question number 1. Compute the quadratic dual of the polynomial algebra in 2 variables where the degree of each variable is 1. Question 2. Prove with all details that each Pi is a simple object of the category of linear complexes. Question 3. Prove that P overlined I has no subdiagonal homology. Question 4. Compute the complexes P overlined and I overlined for all I for the Quiver algebra, where the quiver has 2 vertices 1 and 2, 2 arrows alpha from 1 to 2, and beta from 2 to 1, and the relations alpha beta alpha is equal to beta alpha beta is equal to 0. And question 5. Show that for the algebra A, which is a quotient of the polynomial algebra Kx, modulo the ideal generated by x to the power 4, the quadratic duality functors are not mutually inverse equivalences. Thank you very much and see you next time.